Okay, so series solutions to differential equations. Okay, so you add this method to the list of methods we had previously. So we had the separable, we had homogeneous, we had linear, we had the method with the Laplace transform. You add this onto that. So these are the 5 methods that you can use in assessments. Okay, you're free to use whatever you want, but like I said earlier, this should not be your first guess. Okay, so what we want to do is try and solve differential equations. Maybe it looks something like this. So like alpha y double prime plus beta y prime plus gamma y equals some f of x, right? So like some second order differential equation. Now the alpha, beta, gamma, they could just be constants, they could be other functions, but we just have something like this. Okay, so how do we try and solve this using a series? So what we do is we assume that y of x is equal to the sum, n goes from 0 to infinity, some coefficient cn, we don't know what they are, but some coefficients, x to the n. Okay, so it's some power series or some Taylor series, but those coefficients are unknown. We don't know what they are. Okay, we need to solve for those. So how do we solve for them? Well, we know what the solution should look like. It will be something like this. So we're going to take this solution for y, substitute it into the differential equation, and we're going to solve for those coefficients. So the idea is to take the series solution sub into the differential equation and solve for the coefficients. So you'll see this quite a bit next year, and if not next year, then the year after. Okay, in maths and some of those electrical engineering modules, you cover this again. Okay, so we're just going to introduce it for some small examples, but the bigger stuff, you will do that next year or the year after, especially the electrical engineers. You see this quite a bit. Okay, so let's have a look at an example. Example 1. So we have y prime minus y is equal to 0. Okay. Now we know that this is very easy to solve, right? It's separable. You can do it in a couple lines. What we're going to try to do is solve it using this way, okay, with the series solution, and we're going to see if it matches up. Okay. So first step, we assume y can be written as that series. So y of x is equal to the sum, n goes from 0 to infinity, some coefficients, again, we don't know what those are yet, x to the n. Okay, so that's our goal. Next, we see in the differential equation, we've got y prime. Now, we know what y looks like, so we can do the derivative of y and then substitute in. So what's y prime going to look like? Okay, so this is just a polynomial, so ignore the infinity, it's just a polynomial. And we want to do the derivative, so we can do the derivative for each term. So this is going to be the sum. N goes from 1 to infinity. So we'll start from 1, because the first term is a constant, the derivative of a constant is 0. So now we start from 1. Then we've got Cn, that's just a constant, it's not going to do anything. Now the derivative of x to the n, take the n down, subtract 1. So this will be times n, x to the n minus 1. Okay, so you just do it term by term. So we've got y prime, cn, we don't know what that is. We can substitute these two in the differential equation and then solve for cn. So let's do that. So this will be y prime minus y equals 0. So let's substitute. So we have the sum, n goes from 1 to infinity, n cn x to the n minus 1. Okay, that's for the y prime. Minus y. So minus the sum n goes from 0 to infinity, cn x to the n, and this needs to be 0. Okay. Now, again, we want to solve for these cn's. Yes? This one. This one is our y. So the y starts from 0. The first term is going to be y prime. But remember, where does the series start? It's a constant plus something x squared, and so on. What's the derivative of a constant? 0. So if n equals 0 is a constant, we do the derivative, it goes away. So we have to start from 1. Okay. But notice, if we do start from 0, n is 0. So what's the first term there? N times Cn, when n is 0, 0. So it goes away. Yeah. So that's our y. Okay. Now, what we want to do is try and put these series together into one series. But there's an issue. The first one has x to the n minus 1. That exponent is n minus 1. The second one has exponents n. We cannot combine them, right? You cannot add x squared and x cubed. That does not work. X squared and x squared, that's fine. So we're going to do a little bit of re-indexing to make both of the exponents the same. Yeah? Oh, sure. Okay, so we're going to do a little bit of re-indexing. Let's call the new index k. And we're going to call that n minus 1. Why? Well, that exponent there is n minus 1. We want to get rid of that, so we call that k. So what happens to the rest of the series? We're going to have the sum from k equals something. What is that going to be? When n is 1, 1 minus 1 is 0, so k is 0. The top stays the same. What about that n? N times Cn. What does the n become? N plus 1. Yeah. So we write that as k plus 1. We shift it up by 1. Then the Cn, that's going to be replaced with k plus 1. Again, we shift it up. And then in the exponents, we have n minus 1. That will just become k. Minus the sum, n goes from 0 to infinity, cn x to the n. Now these are the same. So term by term, they're the same. We're going to have a constant on the one side, constant over there. We're going to have x to the 1 and x to the 1, x squared and x squared. We can add them together. Now, if the k is bothering you, you can just write it as an n. So this is going to be the sum. N goes from 0 to infinity, n plus 1, cn plus 1, x to the n, minus the sum, n goes from 0 to infinity, cn x to the n. Okay, or you can leave it as k if you can follow along. Otherwise, you can rename it back to n. Okay, and again, term by term, they have the same exponents. So it will be x to the 1, x to the 1, x squared, x squared. So we can combine them. So this is going to be the sum. N goes from 0 to infinity. We'll put a big square bracket just to combine everything. So we have the first coefficient, n plus 1, cn plus 1, minus, and then the second coefficient, cn. Close the big square brackets, and then we have x to the n. Okay, and this is still 0. Okay, on the left, we have some polynomial. On the right, we have 0. So what can you tell me about the coefficients of that polynomial? Yeah, polynomial, it will be x to the 0, x to the 1, x to the 2, but on the right, it's 0. So what do those coefficients have to be? They must all be 0. Exactly. So all the coefficients on this left-hand side must be 0. And that gives us a nice equation for the CNs. So we have n plus 1, Cn plus 1 minus Cn is equal to 0. Okay. We have a recursive sequence. We saw those before. Okay. So we're going to have some starting term, C0. That's the start of our recursive sequence. And then we have this recursive relationship for the next one. So we have C0. We want C1. So we let n be 0. We can solve for C1. We can let n be 1. We can solve for C2. Okay. Like we did before with the recursive sequences. So we have a recursive sequence of Cn starting from C0. Okay. And it's exactly the same as those sequences we looked at previously. Okay, now how do we solve for them? Well, exactly like what we did last time. We start with C0, and then we try to find C1. Once we have C1, we can then find C2, and so on. Okay, so here we can write Cn plus 1 is equal to, we can take the Cn over to the other side, and then divide by that n plus 1 we have in front. Okay, and again, we start from C0. Okay, or you can say start from n equals 0. It's the same thing. Okay, so let's write out a few terms, and then we try to find a pattern. Okay, so C0 is just C0. That's our starting point. What about C1? C1, what do? There we put in n equals 0 on that left-hand side. So we're going to have C0 over 1. Okay, what about C2? What's C2 going to be? On the left there, we let n be 1. We get C2. So we're going to have C1 over 2. Okay. But C1 is the same as C0. So we can write this as C0 over 2. Okay, what about C3? So we look at the left-hand side. We want C3, so n must be 2. So we're going to have C2 over 3. What is C2? Right, we want C2 over 3. C2 is C0 over 2. So it will be C0 over 6. Okay, and then you can carry on the pattern there. Okay, what we end up with, if you carry on the pattern here, is that Cn is equal to C0, because we always have that at every step. And then the bottom just becomes n factorial. Right? Because it was 1, 1, 2, 6. Next one would be 3 factorial, 4 factorial, and so on. Yeah, so just check that. All of those denominators there are just this n factorial. Okay, so 3 factorial, 2 factorial, and so on. Okay, which means we have our coefficients we want. Our coefficients are just C0 over n factorial. Yes? The C0 over 6. So I'll do that out here. So C3 is C2 over 3. You fine with that step? But what is C2? We look at the previous line. That's C0. Can you see the pink? The previous line, C2 is C0 over 2. And then a half divided by 3, 1 over 6. And that one is that one there. Okay. Yeah, please be very careful when you do the sequence here. Because if you make a mistake with C1, now C2 is wrong, C3 is wrong, it goes bad. Okay, so we've got the coefficients, and we can write out the solution. So this is going to be the sum. N goes from 0 to infinity. The Cn, which we know now, And then, so that's a factorial there. And it was x to the n. But C0 is a constant. We can take it out of the sum there. And we're left with 1 over n factorial x to the n. What is that? E to the x, yeah. Okay, that talking needs to stop. Okay, so that's C0 e to the x. Okay, now if we go back right to the beginning, over here, we could have solved this in like a couple lines, right? Because this is going to be dy by dx is y, dy over y is dx. So we get the logarithm, take it over to the other side, we get y equals a e to the x. Right? Couple lines using the separation of variables, maybe a page using this method. Yeah. Yeah, but we get the same answer. So it's just another tool that you can use. Now, when would we use this and when would we not use this? So for very simple examples like this, with the y prime minus y equals 0, you wouldn't use this. You would use something else. However, we'll see later and in the tutorials, there's some equations that we can't solve directly. So these ones, we can integrate, we get an answer. Some of them you cannot integrate. There's no antiderivative, and you're forced to use this method. Okay. In the tutorial, you'll see there's one example like that. The other ones you can integrate and you get nice answers like this. Okay. Any questions? Okay, so again, you can always use this method, but most of the times it'll be easier using those other 4 that we went through. Okay, any questions? All good. Okay, example number 2. So here we have y prime minus y equals x. What type of differential equation is this? Linear. Yeah, it's linear. So you would use the integrating factor. So for homework, solve it using the integrating factor and then compare it to what we do with the series method. So homework, solve using integrating factor. I'll just write the mu, you know what that means, and compare. Okay. So let's go through it. So we assume a series solution. So we have y of x is equal to the sum. N goes from 0 to infinity. Some coefficients we don't know, x to the n. Okay, so that's taking care of the y. Next, in the differential equation, we have y prime. So we have to do the first derivative. So we have y prime of x is equal to the sum. N goes from 1 because the first term was a constant. The derivative makes it go away. N Cn x to the n minus 1. Now there's no second derivative, so we just stop here. In the tutorial, there's some examples with the second derivative. You'll look at that later. Okay, so we're going to take the difference, and then the right-hand side, that's x. So we have the sum. N goes from 0 to infinity of that y prime. So that's our first term. So that'll be 1. Minus, and then we have y, so that will start from 0. Okay, and then that right-hand side, that's x. Okay. Everyone clear with that? Okay. Okay. Now we're going to do the same trick as before. We do the re-indexing so that they have the same exponents. So re-index the sum to have matching exponents. Okay, so the first one there is n minus 1, the second one is n, they don't match up, so you re-index the first one so it matches with that second one. Okay, so what do we end up with? We're going to have the sum, n goes from 0 to infinity. We can put a big square brackets to put all the coefficients together. So this n, that's going to become an n plus 1. The cn, that will be a cn plus 1. X to the n, we're going to take it out of the brackets there. Then we're going to have minus cn. Okay, for that coefficient there. Everything to the power n. Okay, so we've grouped everything there. And that right-hand side, that's still x. We can put a x to the 1 there. Okay, so let's look at the left side and the right side. So on the left side, we're going to have n equals 0 as our first term. That will just be some constant, right? Because x to the 0, that's just 1. On the right-hand side, do we have anything like that? No. So that must be 0. Okay, what happens when n equals 1? We're going to have some constant times x. And on the right-hand side, do we have something like that? We don't. Yes? No? There's x. Of course we do. Look, when n equals 1, we're going to have 2 times c2 minus c1 x to the 1. On the right-hand side, we have 1 times x to the 1. Did everyone see that? Okay. So that coefficient must be 1. What about n equals 2? On the left-hand side, that will be something x squared. On the right-hand side, do we have that? No, so that must be 0. What about n equals 3? The left-hand side will be something x cubed. The right-hand side? Nothing, so that will be 0. Everything after that will also be 0. Did everyone see that? Yeah. So let's write it out. So n equals 0. Okay, so when n is 0, let's see what we have on both sides. So n is 0, so we have c1 minus c0. And then on the right-hand side, we got nothing there. So that's just 0. Yeah. What happens when n equals 1? Okay, let's look at the side there. So n is 1, so we have 2c2 minus c1. Okay, so that was the n equals 1 case. On the right-hand side, what do we have? Just x. So what's the coefficients of x? 1. So that must be 1. Okay, n equals 2. And we can continue the pattern and then solve. So n equals 2. We have 3c2 minus c, so that's a 3, minus 3, 2 equals. This one would be quadratic. On the right-hand side, we don't have anything like that. So that must be 0. And the same for all the other ones. Those are all 0. Okay. And you can continue the pattern there. So all of those will be 0. Okay. So you can just solve it. Very easy to do. So here, this first one, the C1 is C0. So you got that. Then you substitute C1, you solve for C2. You substitute C2, you solve for C3. And you just go carry on like that. Okay, so just go through that. And you'll see the following. So we have C0. Then we have C1 is also C0. That's from the first equation there. And so on. You can carry on with that. Okay, and then we have, I'll give you C2 and then you can do the rest for homework. So C2, that will be C0 plus 1 over 2. And you can do the rest there. Okay, does everyone understand how to get those? Yeah. Okay, so we got all of our, okay, that carries on there. So we got all of our coefficients. We can substitute into that beginning equation here. And we get our answer. Okay, so what's that going to be? Y is equal to, y of x is equal to the sum. N goes from 0 to infinity. Cn x to the n. Okay, and then we just substitute what we have there. So this is going to be equal to C0 plus, and then C1 is also C0 plus, and then you can add in the rest. That will be the sum. N goes from 2 to infinity. We're going to have C0 plus 1 over n factorial x to the n. Okay, so you check that. That last term there, you just continue the pattern and you just double check that. Okay, a little bit of simplifying now. So the C0, that can stay. C0x, that can stay. What's this going to be here? We can take out that C0 plus 1. That's just a constant. Then we have the sum. N goes from 2 to infinity. 1 over n factorial x to the n. What's that going to be? Not e to the x. Close. Remember, we're starting from 2. So it won't be e to the x. It will be e to the x minus some stuff. So n equals 0, we're missing, and n equals 1, we're missing. Okay, so let's check what that's going to be. So here we have the sum. N goes from 2 to infinity, 1 over n factorial x to the n. What are we missing to make it e to the x? We're missing n equals 0, so that we need to add a 1 there. Okay. And we're also missing n equals 1, so we're missing the x. So if we put those back, then this will be e to the x. Okay, please just keep in mind, the Taylor series, they start from n equals 0. If we start from n equals 2, then we're missing some things here. Okay, we need to add them back. So let's substitute that, and then we got our answer. So this is going to be C0 plus C0x plus C0 plus 1. And then this whole series there, that will be e to the x, and then we take that stuff over. So that will be e to the x minus 1 minus x. Okay, we just take it over to that side with the exponential. Okay. And then finally, we can write out our solution. Y of x. Okay, that's just simplifying, right? Just expand the brackets there. So that will be y of x is equal to C0 plus 1 e to the x minus 1 minus x. Yeah, we end up with that. Or if the C0 plus 1, you don't like that, you can write it as a e to the x minus 1 minus x. Yeah, and then this, please check with that linear method from before. So check this for homework. All right. Any questions? No questions. Okay. Some homework problems. Okay, so you'll have these 3 homework problems as well as the 5 from the tutorial. Okay, so number 1, x y prime minus y is equal to x squared. Okay, and then just to check your answer, that should be y equals cx plus x squared. Okay. Then number 2, x y prime minus y is equal to the natural log of x. You should get y equals cx minus the natural log of x. I'll give you a hint for that one in a bit. And then number 3, y double prime minus y is equal to x. Okay, so that's a second derivative there. So in that previous example where we had y prime, you're going to have to do the derivative a second time, okay, to get that. Equals x, and you should get y is equal to a e to the x plus b e to the minus x, some unknown a and b, minus x. Okay, and then just a little hint for number 2. Okay, so when you substitute the y and the y prime, that left-hand side there, that will be some series, right? With the c ends. That right-hand side is just log x. Okay, so if we've got a series on the one side and log x on the other side, how can we compare them? Okay, so the left-hand side, that will be a series. The right-hand side, that's just log x. We want to compare the both sides. Yeah? No, not e. Yeah? Nope. We have a series on the left side. We've got log x on the right-hand side. We want to compare the coefficients. What can we do with the log? Okay, there's your hint. Series on the one side, log x on the other. What can we do? Yeah? Change it to a series. Exactly. So hint, writes log x as the sum. N goes from 0 to infinity. Sum coefficients x to the n. So the left-hand side, that will be a series. The right-hand side, that will be a series now. And then you can compare the coefficients. Yeah. So before, that right-hand side would have been 0. So all the coefficients are 0. But if that right-hand side is non-zero, then you need to compare the coefficients of the two series. All right. Any questions? Yeah. The example 2. The cloud one, yeah? Yeah. Okay, sure. So this series over here, we want to work out. It's almost the exponential, but the problem is this bottom is 2. So there we're starting from 2, which means we're missing n equals 0 and we're missing n equals 1. So we need to add those back. So we have the series starting from 2. What is the term for n equals 0? 1. So we add that. What's the term for n equals 1? X. So we add that. So now we add in the missing terms. So now there's nothing missing. So it is e to the x. Yeah. So we're just adding in the missing terms to make it e to the x. So here you can make a note. Add in the missing terms. Okay. Any other questions? You're good. Okay. So for your class test 4, remember that will be on the Taylor series applications. So finding the limits. You know that limit like we did in the quiz. So that one and this one, that will be the first 2 questions for your class test 4. Class test 3, that stops at interval of convergence. Yeah. So interval of convergence, that's it for your class test 3. This stuff now, that will be the beginning for class test 4. Okay, so don't mix them up, when we get to the revision. Okay, any questions? No. Okay, cool.